In this video, we're going to have one-dimensional motion, linear kinematics in physics, sometimes called rectilinear motion, explained to you today here on High Peak Education. Hello everybody, hope you're doing really well. Wanted to give you this intuition video which runs you through 4 simulated experiments of how one-dimensional motion, that is motion in a straight line, sometimes called linear motion or motion under constant acceleration in physics, is described. We're going to help you through to understand what the position versus time, velocity versus time, acceleration versus time graphs look like. We're going to help you develop the equations, or at least the intuition, somewhat in your mind. And we're also going to give you several examples of how to identify what that motion really looks like. We're going to be discussing vectors and directions, but remember, in one-dimensional motion, vector directions are only given by the positive and negative directions. That is, to the right or to the left. That's all that really matters as we keep track of the directions here. So we will discuss things that don't require a direction, like speed and time, but vector quantities, position, velocity, acceleration, are all going to be discussed in today's video. So without any further delay, let's get into today's experiments. Shown here, we have an inclined plane with a ball. And let's assume that this ball rolls without slipping. That is to say, there's friction enough that the ball grabs onto the inclined plane, but at the same time it doesn't slip otherwise, and it doesn't have any other friction. So the ball rolls very nicely. Let's also assume we have the velocity versus time graph plotted here. Velocity is on the vertical axis and time is on the horizontal axis. And we're also going to show here the velocity of the ball in terms of like a speedometer, but this will be in meters per second. What we can do is we can control the angle of the incline of this inclined plane and then measure what the height of the ball is before we release the ball. Now, very similar observations were made by Galileo Galilei, who, being over in Italy in the Renaissance, was an important scientist and observer of the motion in physics. And based upon Galileo Galilei's findings, Sir Isaac Newton and others came after him and came up with many more observations which help us now to understand our current understandings of physics, and certainly the basis of how we understand motion. So what Galileo Galilei realized was that when he would roll the ball down the hill, or he would release it to roll down the hill, he noticed that over time the velocity would increase. And this seems pretty reasonable, probably very similar to your intuition. That is, when we let the ball roll down, and by the way, Galileo didn't have access to strobes, but we do. So strobes are going to be at regular time intervals. In fact, at half-second time intervals, we'll set it at. We'll take a picture of the ball's current position, and we'll see how the ball progresses in terms of its motion. So if we release the ball, notice every half second, the strobes are getting further apart. And let us think about what this means in terms of motion. When the velocity is increasing, that is to say, the ball is speeding up. Notice that there is a positive slope in the velocity versus time graph, and that signifies that with time, not only is the ball moving, but it's actually moving faster. If you watch this one more time, hopefully you'll see that over here in the sort of this speedometer, that the velocity indeed does increase with time. So this is something that Galileo noticed. But then he repeated the experiment by saying, well, what if I set up the ball to be at a 30-degree angle? So notice that, first of all, the height is larger. Secondly, we're going to plot this velocity versus time on the same graph, And we'll show the speedometer again, and let us allow the strobes every half second. Well, if we play this, notice that this time the strobes are even further apart than before, and that's because the slope of the velocity versus time graph is larger. That is to say, there's a greater increase of velocity with respect to time. Notice that the final velocity that the ball gets down to the bottom of the inclined plane with is larger than it would otherwise have been for a 15-degree angle. And notice this is a notion of what we would call acceleration. So notice that if we play this again, notice that there's greater acceleration to the ball. What do we mean by acceleration? Acceleration is the change in velocity with respect to time. So if velocity changes your position where you are, that is, gives you motion in the universe, acceleration increases or decreases your velocity with time. Acceleration can also change your direction, but we will not cover that, at least in these videos and in similar lectures, for a while. Notice that the acceleration is positive, that is, the velocity is getting greater with time, and it's also larger as we increase the angle. So if we go up to a 45-degree angle, before I click play, I hope that you can predict what's going to happen. Okay, so the strobe should be further apart from one another in half-second time intervals. The ball should be moving faster at the end of the inclined plane than before, and the slope of the velocity versus time graph should also be steeper. Notice the initial height now is 22.06 meters for this inclined plane. And this is indeed what we observe. We observe the ball is going faster and faster as time proceeds, but it's also going faster than either of the previous two experiments. So these were some of the first experiments performed on motion by Galileo Galilei, trying to quantify motion and put numbers to it. Now, from there, we learned much about the study of motion, namely kinematics, and in a later video, we'll actually introduce the calculus that goes along with it. But for now, we're going to look at another example, this time specifically of a car moving along a horizontal axis, that is an x-axis, and we're going to take a look at its motion for various numerical values that we can put in for position, velocity, and acceleration. So let's take a look at that. So now what I have shown here is a car on a horizontal x-axis, and this axis will show us the position of the car, and we'll measure it as a function of time. Notice that the position, that is x, will be plotted as a function of time simultaneously. Notice also we will plot the car's velocity versus time and its acceleration versus time. Notice the units of position are going to be in meters. The units of velocity are going to be in meters per second. The units of acceleration will be meters per second squared. Those are the SI, or International System of Units, standard for position, velocity, and acceleration. Note that the position will be denoted in red, that is, this curve will be a red line. The velocity will be shown in purple, and then also the vector, which is the arrow which is sort of showing you the motion of the car sort of attached to the car, will be also in purple, and the acceleration will be plotted here in blue, and then later when we re-show the experiment we can show the acceleration vector, which is going to be a blue arrow that's sort of attached to the car. Furthermore, we will measure the elapsed time of the car during this entire experiment. In fact, we'll do several experiments. And we can measure the time that it passes this green photo gate, which will be at 25.000 meters. And we can measure the time that it takes to pass the red photo gate, which is at 50.000 meters. Note, by the way, it's when the front bumper of the car passes each of those photo gates. In fact, we say that the car is at 0x position initially right now because its front bumper is exactly at 0 meters for its initial x position. What we can do is we can control the car's initial position, its initial velocity, and its initial acceleration. And what we can do is we can reset to perform a different experiment, and we can also slow the motion down by 10 times so that you can see what the motion is in more detail. Okay, so if we start off everything with 0, if we press start, notice that this is completely boring in terms of its motion. That is to say, the position as a function of time does not change, it stays at 0. The velocity is 0 the entire time, and the acceleration is also 0 the entire time. And the clock is moving forward in seconds as elapsed time. So that's absolutely completely uninteresting. So let's have something a little more interesting go on. Let's start the car at 0 initial position, but then let's give it an initial velocity. Let's say 5 meters per second for its initial velocity. Now let's think about what's going to happen with the car. In fact, let's see if we can predict what these graphs should look like. I don't think there's going to be any acceleration. It's going to be probably easiest to predict here from right to left. The acceleration should be 0 the entire time because, well, we set the acceleration to be 0 and that's not going to change. The velocity should be up here at 5 meters per second, and that should just be a nice constant function, a horizontal line at 5 meters per second. That is an unchanging constant velocity. But how about the position versus time? I think it's going to be a constantly sloping upward line. The slope of that line will be 5 meters achieved every 1 second, because that's going to be 5 meters per second for the slope, and thus also the slope of the position versus time graph being the velocity, that is 5 meters per second. And I think this vector arrow is going to be a constant because, again, the velocity does not change. But notice also, how long is it going to take us to get to this green photo gate? Well, I think it should take 5 seconds exactly because it's 25 meters away. And this red photo gate, 10 seconds. Let's see if we can verify this with the experiment. So notice the acceleration is 0 the entire time. The velocity is 5 meters per second the entire time. And the slope is a nice constant slope, position versus time. And notice that it did take 5 and 10 seconds to reach the green and the red photo gates. Okay, I hope that makes sense to you, and that should hopefully not be too difficult. Many of you have probably seen constant velocity problems in your life. Let us reset, and then now let's make one change. Let's give the car an initial position of 10 meters. Now before I hit enter, what do you expect to be different about these graphs and about the motion? Well, hopefully you know the acceleration should be the same, because I don't think it's going to accelerate at all. How about the velocity? Well, it should also remain the same. Why is that? Because again, we're not changing anything about the velocity. It should be a constant function at 5 meters per second. But how about the position? The position, I think, should start at 10 meters. So in other words, the vertical axis intercept will start at 10 meters, but will have the same slope as before. So now if I hit enter, you should see that its initial position is indeed 10 meters. Look at this, the car is going to start at 10 meters. When we start the experiment, it looks just as before, except two things. Number one, there's a vertical axis value for the position that is 10. Some of you in math class would call this the y-intercept, but don't call it the y-intercept. Call it the vertical axis intercept. And then notice that it takes only 3 seconds to get to the green photo gate because I think the car only had to go 15 meters. And now it only takes 8 seconds to get to the red photo gate. So those are the changes that we observe. And I hope this makes sense as I walk through this. Please let me know in the comments if this is making sense or if you have questions about this discussion. I'll try to answer them. Now let's try a slightly more interesting and a slightly different experiment. Let's make the initial position 0 again. Let's go back to 0 initial velocity, but let's give it an acceleration of 1 meter per second squared. Okay, now we need to make predictions again. What should the acceleration versus time graph look like? Well, now it's not going to be 0 because we're making it have an acceleration. I think it should be a constant function here in blue at 1 meter per second squared. How about the velocity versus time graph? Well, I don't think the velocity is going to be constant with time any longer. I think now it should have a slope, but the slope should probably be 1 meter per second gained each 1 second. How do I know that? Well, because the acceleration is going to be 1 meter per second squared. So if you gain 1 meter per second velocity each 1 second, that's meters per second squared, and that's the slope of the velocity versus time graph. And how about the position versus time graph? You really have to think about this. So at first, the car is going to gain very little position. But then as time goes along, it'll gain more position, and then even more position, and then even more, and it should go up. Now, by the way, you might say it should go up exponentially. That's not quite the right word. That would be a continuous change of the position versus time. Continuous in the sense of that it's constantly, as it goes faster, its position goes further faster. I think it should actually be quadratic. Why quadratic? Well, because if you look at a certain equation of motion called the displacement curve has a t squared in it. And that gives rise to a quadratic function of position versus time. And then that will indeed give us the shape of this curve. And by the way, quadratic will actually be a parabola, should be the right-hand side of a parabola, which you've hopefully seen before in your math classes. So let's hit the enter key. So again, the car is back at 0 initial position. It's got 0 initial velocity, and it has no velocity vector to start. And then it starts off with 1 meter per second squared for its acceleration. That should be constant. Its velocity starts at 0. Its position starts at 0. But this should have a constant slope. This should be a quadratic with positive upward concavity. And it should be looking like a parabola. So let's hit start. So look at this. The acceleration is constant with time. The velocity is sloping upward with time. Look at the position versus time. Indeed, it is quadratic. Now let's reset, and then if you looked at the graphs the first time around like I did, look at the car. If you looked at the car the first time around, look at the graphs. So let's start this again. Now look at the car. Look at the velocity vector. Do you see how it's getting longer? And in fact, it's constantly getting longer with time. That is to say, the velocity is increasing with time. There is an acceleration. Now, by the way, you may ask, how did you know how long that it took to get to the green photo gate? Well, it turns out that requires a kinematic equation. The kinematic equation for 0 initial velocity would actually be 1/2 a t squared. It turns out that since 1/2 at squared equals the position change, if the position change is 25, and then a is 1, 1/2 of 1 is 0.5, t squared, notice that 7.071 seconds. Let's think about this. So if we have 25 equals 0.5 t squared, we could multiply both sides by 2 and get 50 equals t squared. Take the square root, we get 7.071.
So that's the square root of 50. And that's what we have for the time. Notice that for 50 meters, the red photo gate, the reason it takes exactly 10 seconds is because we would multiply by 2. So we would get 50 times 2, that'd be 100. Take the square root of 100, we get exactly 10 seconds. Now, by the way, if you're not familiar with those kinematic equations, don't worry about that. I will be covering that in later videos. But just to give you a sense of, that's not necessarily obvious when the acceleration is not 0. Let's reset this and let's change it to 2 meters per second squared. So I think the car is going to speed up even faster. And the acceleration is going to be a constant function at 2 meters per second squared. You'll have what? A steeper velocity versus time graph. And I think that the parabola will rise even faster. It'll have a more steep concavity to the quadratic function. Look at the velocity vector too. It's increasing much more quickly in its length. That is, its magnitude, as we have now a larger acceleration. Notice also it took even less time to get to the green photo gate and the red photo gate. And again, you could calculate those using 1/2 a t squared. So t here is going to be 5 because I think 1/2 times 2 times 5 squared is going to be exactly 25. And then 1/2 times 2 times, this is again square root of 50 squared, should be 50. What if we do something even a little more interesting? Let's give the car an initial velocity that is, let's say, positive, say 10 meters per second, and let's give it an acceleration of 1 meter per second squared. Now you should try to think about what's going to happen. Okay, so the acceleration is going to be constant at 1 meter per second squared. The velocity is going to be starting at 10, but have the same slope as the experiment 2 experiments ago. The position is going to start off at 0, but I think that it will achieve greater positions faster because it starts off with an initial position that's 0, but it starts off with an initial velocity. So it's not going to be a parabola that starts sort of horizontally. It's going to be starting with a parabola that's already sort of sloped up. Let's go ahead and see if we can hit enter, and let's observe this. So look at that. The car started off with an initial velocity, and it's accelerating, so it goes really fast. And by the way, you may ask, how can you calculate the time to the green photo gate or the red photo gate now? Well, it turns out that's difficult to do if you don't use a kinematic equation, like the displacement curve. That is, delta x equals v initial times t plus 1/2 at squared. And again, you wouldn't necessarily know that unless I told you, but we'll cover that in later videos. And let me know in the comments if you want to see those equations shown up here on the videos throughout these videos. Let's try something I would think would even be a little more interesting. Let's give the car an initial velocity of 10 meters per second, but let's give it an initial acceleration of -1 meter per second squared. Now you should really try to think about what's going to happen. Okay, so the acceleration is going to be at -1, again, a constant function the entire time. By the way, for this particular set of experiments, we only allow for constant numbers for the acceleration. Otherwise, there'd be a non-zero jerk, which means the acceleration would change with time. Many motions in this world are actually constant acceleration motions, and that's all we're allowing for in this experiment, so it'll be -1 meter per second squared. How about the initial velocity? Well, it's going to start up here at 10 meters per second, but now the slope should be negative. Not positive, but negative. It should slope downward because the acceleration is a negative number. Now, what's going to happen is it's going to cross the time axis. That is, the graph will. And what's going to happen there? Well, the velocity is going to be 0. What should the car do there? It should stop. It should stop because the velocity is 0. And in fact, When it stops, it'll then stop and then start moving back to the left. Why to the left? Because we're still going to have a negative acceleration, and the velocity is now going to increase towards the left after the car stops. But then also, what about the position versus time graph? Well, I think the position is going to increase as we go along to the right at first, but then when the car stops, it'll reach its maximum position to the right, and then it'll start moving back to the left. So I think this parabola is actually going to face downward. It'll be sort of a downward facing parabola, negative concavity, and the top of the parabola, which many of you know to be the vertex of the parabola, that should be the point where the velocity is 0 and the car has reached its maximum rightward position. So let's hit enter and let's try this experiment. Notice the car is moving to the right and its velocity vector is getting shorter. That is, this purple arrow is having less and less length. Notice that it takes 10 seconds to reach this red photo gate. Notice it's now going to move back past the green photo gate, so it's going to register the time that it went past the green photo gate a second time. But did you notice that the car was moving to the right at first, and then it was slowing down because the acceleration was negative the whole time, but then the car started to move to the left and started to speed up towards the left. That's what it means to have a negative acceleration. Let's reset this, and again, if you watch the car the first time round like I did, watch the graphs. Again, if you watch the graphs the first time, now watch the car. So let's do start. Look, the acceleration versus time is indeed constant at -1 meter per second squared. Look at the velocity. It's sloping down. It's about to cross the time axis. Look at that, right at 10 seconds, just like we see here. And at 10 seconds, the car reaches its maximum position. Look at this. At 10 seconds, we get to the vertex of the parabola, and that is when the car has reached its maximum position, its velocity is 0, it's a downward-facing parabola, and indeed, the car starts to accelerate now to the left. So one thing I hope that you see is a theme for all of these experiments. The slope of the position versus time graph is the velocity. Here we have positive slopes on position versus time. Here we have positive velocities. Here we have 0 slope, that is a horizontal slope. Here we have 0 velocity. On this side we have negative slope. Here we have negative velocity. And what about the slope of the velocity versus time graph? Well, it's only constant slopes, but if the slope is negative, the acceleration is negative. And if the slope was positive, the acceleration was positive. And in fact, the slope of this line is -1 meter per second gained every 1 second. So it's actually 1 meter per second lost each 1 second. But again, it's a negative number. By the way, this whole business about positive and negative numbers means that all these quantities, position, velocity, acceleration, are vectors. Vectors mean they have direction. To the right means positive in the positive x direction. To the left means negative, the negative x direction. So if you change your position to the right, that's a positive position change. Change your position to the left, it's a negative position change. If the car is moving to the right, positive velocity. If the car is moving to the left, negative velocity. If the car is speeding up to the right, or if it's getting rid of its negative velocity and the accelerations to the right, then those are both positive accelerations. But just like we saw here in the last experiment, the acceleration was negative the entire time. And so you're slowing down a positive velocity and then increasing a negative velocity to have a negative acceleration. In fact, let's watch that last experiment one more time, but this time I'll show the acceleration vector. So the acceleration vector is in blue, but notice that as the car moves along, the acceleration vector does not change the entire time. That negative acceleration the entire time slows down the positive velocity. And then after the car stops, it speeds up the negative velocity. In fact, when the acceleration and the velocity are in the same direction, you speed up. When the acceleration and the velocity are in opposite directions, in terms of their vector directions, their arrows, you slow down. And by the way, how long does it take to get to the red or the green photo gate? Well, that depends, and in fact, it depends upon how long you are going, and it depends upon really a kinematic equation for you to actually calculate that. Now that we've explored this motion at constant acceleration business, I'd like to look at one more simulation that allows us to actually do this where we have more control over the particle. Now, by the way, the car was the particle before in this experiment. Previously, the ball was the particle with the Galileo experiment. The new particle, where we're just going to place a dot and track the motion of the thing, is now going to be a moving man. And the man's going to move side to side on an x-axis. So let's have a look at that one now at this time. So what I now have here is a particle that is a man, the moving man in fact, that can be directly controlled by us. And then the position, velocity, and accelerations are plotted immediately as we move the man around. So let's see if we can click on the man and actually cause him to move. Okay, so notice that if we move the man to the right, notice that his position is increasing, that's in blue. Notice that when we moved him fast at first, the velocity increased very suddenly. Now that he's stopped, his position is no longer changing in time, his velocity is no longer changing, and there's also no acceleration. So let's in fact try to do as best we can a small, slow, constant velocity as this man is moving. Okay, so let's click on the man. Let's get this going with a nice constant velocity. And notice that is the position is increasing with a nice constant slope. Here, the velocity was roughly constant. What do I mean by roughly constant? Well, I can zoom in, okay, and you'll see that it's roughly constant, okay? It's very difficult to get a perfectly constant velocity with time. Even if you're driving your car, hopefully you know it's very difficult to maintain an exactly constant velocity. Now, by the way, the closest thing you could probably imagine to this is cruise control, which tries to keep your car at roughly a constant velocity. That is, if you're not changing direction, by the way, on a road. Or perhaps a self-driving car could perhaps do that pretty well. But in practice, it's very hard to do to get the velocity exactly constant. Notice the acceleration as well. When I first caused the man to speed up, the acceleration was not zero. So hopefully you see that. The acceleration was not zero. The acceleration was also not entirely zero as he was moving along. Again, it wasn't a perfectly constant velocity. But notice that when the man stopped, so right around here, right around this 3.2 seconds or so, when I allowed him to stop, the velocity went down very suddenly and the acceleration was negative, and it's very largely negative at very quickly, okay? Now I'm going to do my best to give a constant acceleration. This is a little bit harder to do, so I'll do my best. So let's see what happened. I want to zoom in on these graphs. Notice that the position versus time was roughly quadratic. Notice that the velocity versus time, it went up roughly linearly. It looks like it's even out of the scale. Yes, it's even out of the scale. Okay, so it's well beyond 10 meters per second or so. Look at the acceleration. Notice the acceleration was positive at first, but then when the man slowed down, it was negative. And notice that basically it's very hard to maintain an exactly constant acceleration. Now, as I said, if you're accelerating in your car away from a traffic light, When your speedometer is going like this, that's roughly a constant acceleration. But you're not going to be perfectly constant acceleration. I mean, again, computer systems can probably do this pretty well, but as humans, we can't necessarily achieve that perfectly. But this is what we mean by having control over a situation. Now, by the way, let's see what happens if we play again. And this time, let's cause the man to accelerate to the left, but let's have him go too far. So let's have him accelerate to the left. Faster, faster. And notice that he actually bumps into the wall here, okay? And it turns out that we crash into the wall. So that's the idea. I mean, when the man crashes into the wall, he is at -10 meters for his position, and he's not going any further. So notice that very suddenly, when he crashes into the wall, the acceleration is positive to the right because his velocity was negative. And let's also note that, again, we accelerated in the negative direction, but then when the man hits the wall, he suddenly stops. So hopefully this gives you a better idea of what slightly more realistic graphs look like of position, velocity, and acceleration. Again, these are vectors, and these are the kinds of motions that we have to analyze when we're analyzing kinematics, when we're analyzing how things move, and we're tracking the particle. Let's take a look at one more time that we look at these graphs, but this time let's try to match some graphs up. That is to say, let's be given sample graphs and see if we can come up with the other graph. So we'll be given velocity graphs, we'll have to match them up with the corresponding acceleration graphs, or vice versa. So now what I have here is a situation where we have a velocity versus time graph, and we need to match it up with the acceleration versus time graph. So we have three choices here, and we can click on the little radio bullet and submit, and then see what happens. So let's look at several examples here. Look at this. The velocity is negative, then it's 0, then the velocity is positive. But to me, it looks like a very constant slope. So if we have a constant slope of velocity versus time, I think that the particle has a constant acceleration, and furthermore, the acceleration is positive because the slope is positive. So let's see which of the graphs that most closely matches. I think it's going to be the second acceleration versus time graph. Let's submit. That's correct. Click next to proceed. Okay, let's try another one. And by the way, for those of you that are first learning these things, you should pause the video, try this at home. Let me know in the comments if this is helpful. So how about velocity versus time, but it's just sloping downward? Again, a constant acceleration, but this time a negative slope, so a negative acceleration. So now I think it's this last one. Submit. That's correct. Let's go. How about this one? Constant slope, where the velocity increases with time, and then constant velocity. So let's think. If there's a positive slope, there should be positive acceleration, but then when we move at a constant velocity, there should be no acceleration. So I think that this is like a car that speeds up from a traffic light to this point and then moves at roughly a constant speed. Hopefully the speed limit. Hopefully none of the viewers out there, you're ever going over the speed limit, right? Here we have the constant velocity. So let's see. I think it's probably going to be this last graph. So positive acceleration, then suddenly 0 acceleration. So that's correct. Let's proceed. Let's try another one. Constant slope of velocity versus time, then 0 velocity and thus 0 acceleration. Now, believe it or not, I think it's actually going to be the same shape as the last one. But that's just negative velocity, but the negative velocity was getting smaller. That is, the only difference in this case is the velocity starts off negative, we slow the car down, and we slow the car down with a positive acceleration, then the car is actually stopped here. So it's the same shape of acceleration versus time, but what you would actually view would look a lot different. Okay, correct? And I think we're back to where we started. Let's switch it up. Let's go acceleration graph. Okay, so now we're going to look at acceleration versus time graphs, and now we want to figure out which is the proper velocity versus time graph. Looks like positive constant acceleration. So this is positive constant acceleration because it's a positive slope. But wait a second. This is constant positive acceleration, and so is this. So part of the reason we're uncertain as far as which graph is because we don't know what the initial velocity was. All we have is the acceleration versus time. Okay, so let's submit that. So that's correct. It turns out it could be any of those. Let's try another one. Here we have constant negative acceleration. So that should be a negative slope on the velocity versus time graph. So that could be the second or the third choice. Again, this is a car that, let's say, starts at rest and accelerates to the left. This is a car, let's say, that's moving to the right, slows down, stops, and then starts to accelerate to the left. Okay, correct? Zero acceleration, I don't think the velocity should change. And again, that's going to be all of these. Because again, the velocity is just constant with time. We don't know what the initial velocity was. Okay, so that's correct. And then let's go next. And notice that we're going to have what? Positive acceleration, then zero acceleration. So positive acceleration, that's constant, should be a positive slope to the velocity versus time graph. Rate, well, no change in acceleration, but also no change in velocity. So I think it's going to be this last one. Positively increasing, sloping up velocity, then constant velocity. Notice this one would be constant acceleration the whole time, but that would actually be the position versus time graph. And it's not just constantly increasing the velocity the whole time. Okay, so that's correct. And now I think we're back to the beginning. Okay, so hope these were helpful. I hope you now understand kinematics, motion in one dimension, position, velocity, and acceleration much better. And now you've had some practice, and now you can understand your physics and motion.
So what we saw in this video from these various experiments are a couple things. Number one, an object maintains its position in the universe if it doesn't have any velocity to speak of. Number two, we saw that if something's moving at a constant velocity, its slope on the position versus time graph is nice and constant, but its velocity remains constant on the velocity versus time graph, v versus t. In each of those situations, the acceleration is zero. But what we saw under constant acceleration is that the acceleration is constant with time, the velocity has a constant slope with time, but that the position versus time looks quadratic. And that comes from the so-called displacement curve, which I will get to in other videos here on this channel. Otherwise, just note that there's lots of different situations where we see linear motion. So when we have a car moving back and forth along a straight road, or when we have a man walking side to side on a sidewalk, or lots of other examples I mentioned. So hopefully you start to understand and connect these ideas together, especially how you can actually graph them and understand the motion. So in physics, we use graphs to help us understand and conceptualize what these variables are doing and how they're changing in time. Remember, this will be called the vertical axis, and then we also have the horizontal axis, because this is not necessarily the y and the x axis any longer. We a lot of times put x or v or a versus t on this axis. And that's often how we keep track of motion in one dimension in physics. So I hope that rectilinear motion, horizontal motion, one-dimensional motion in a straight line under constant acceleration, and kinematics now makes sense to you. So let us know in the comments how you're going to use this information to understand motion in your physics class or in your daily life when you're analyzing motion. We would love to hear from you what other videos you want to see on the channel, and thank you for watching High Peak Education. Please smash that like button if you enjoy this content. Please share this video amongst your social networks, and please subscribe to the channel to grow the channel. You can feel free to support us online. We have social media links in the description and also Patreon. Thank you very much for your support of this channel. We look forward to hearing from you, and we will see you in the next video.